Hello everyone, can you hear me? Okay, okay. So today I will give you a demonstration of PLECS software. So first, click on this PLECS icon. Now it opens the library browser. Now click on File, New Model, and the file opens. So let's keep them side by side. The PLECS library browser and this untitled model. So we will first simulate a basic RLC circuit, and we will see that how the simulation happens and how to capture waveforms, how to see waveforms, etc. So let's go to these. These are the various libraries. So first go to electrical blocks. In electrical, let's go to sources. So first let's take a voltage source. This, then let's take passive components. Take an inductor. Let's take capacitor C like this. Let's connect like this. Just drag the line and it gets connected. Now let us set the values. Let's take 10 ohm. This is 0.001 Henry, that's fine. And this capacitor value is 100 microfarad. Let's keep it a little bit smaller. Let's take 10 microfarad. Let's now take one switch. Just if I search here, it will go. So let's take a manual switch. So manual switch means you have to just okay, let's not take a manual switch. Let's take a proper switch like this, and let's just drag the switch and keep it here, and it connects itself. Now let's take a step input and step. Now this step and step time will give 0.1, initial is 0, final out 1. Let's connect with the switch terminal so that at 0.1 it actually connects. So the switch is open when the gate signal is 0, otherwise it is closed. So when I'm giving the step input at 0 it is 0, at when it's 1 it becomes 1. Now let me put a scope here, file, scope, I will search here, scope. So let's put a scope, and let's also take probe. So this is a very important block, probe and scope. So this is where you see the let's add multiple channels. So go to scope parameters and number of plots. Let's give it 3 plots like this. Fine. Now let's copy the probe. If you just hold Control and drag, then it copies itself. Now if you put Control Shift N, it, the name gets hidden. Like probe is probe, that name is not in. For scope, let's say click Control Shift and N together, then the name disappears. See, and Control Shift and Control Shift N. It appears and disappears. Now let's connect these probes like this. Now let's say I drag this and put it on the probe. So what happens that I can then see its output. Let's component signal is there, so I click on the output. So you can see the output from here. And now let's see the current. DC source current is here. Let's see the source current from here. And let's say I want to see the capacitor voltage. So I will copy paste the capacitor here. Let's check the capacitor voltage like this. Now I will just simulate this. For simulation, let's go to simulation parameter. So this is time span. It is 0 to 1. It will simulate time, and maximum step size is there. There are two modes: variable step and fixed step. So variable step is good enough for this simulation, and 1e minus 3 is also good enough. If you want a very good accuracy, you can put 1e minus 6. but it becomes slower. It will actually simulate very slowly. But if we put 1 in minus 3, it simulates very fast. Okay. Let's for this application, let's put 1 in minus 6. And now we'll open the scope and we'll simulate. For simulation, either you can click on the start or control plus T as you can see here. So what I will do, I will just open it and I will do control T. See, it has simulated control T. Simulation is done. Now we will zoom in and see what is happening. So let's just zoom here. So if you click on here and you zoom, let's see, you can see. Now you can see that this is a second order response you see here. So whenever the switch opens from 0 to 1, there is an oscillation in current. The current oscillates a little bit and it then settles down to 0, and the capacitor voltage rises and follows an underdamped response. Okay, now if I you can see that it happens so fast that you cannot even properly see if it is unzoomed. But if you zoom it, you can see it. Now, how to actually make this actually smaller? Let's say, yeah, I want to make this slower, not smaller. I want to make this slower. Let's say it should go like this. So what I will do, I will increase the resistance value. Let's say I give 10,000. Now let's see what happens. Now you can see that it has become very slow and not 10,000. Now if you know 10,000, let me give 100. 100, what is happening? You see. Now see at 100 also it is very slow and it has become now see that it has become an overdamped response, right? There is no overshoot. Overshoot is completely off. Now to again bring back the damp means under damped nature, let's increase the inductance a little bit. Let's see what happens. See, after increasing the resistance, it becomes under damped again, and now it is visible a little bit. It is not so fast and it is like this. Now if I increase the capacitance value, let's keep 100 minus 6. Let's see what happens. Now see, it again becomes uh, overdamped, right? So now let us increase the inductance again. Let's keep 1, and now we'll see what happens. Now we see that it has become again underdamped, and this oscillation frequency of actually this natural response is now very low frequency. That's why it is so slow and it is clearly visible. So this is a basic demonstration of PLECS software of and also how we simulate RLC network and how we use probe and scope, etc.